Alright, hi, welcome back to Mr. Greenberg Physics without Mr. Greenberg. So today we're going to be attempting number 45 of the homework problems. It's on page 50, it's chapter 2. So it gives us that a certain free-falling object requires 1.5 seconds to travel the last 30 meters before it hits the ground. From what height above the ground did it fall? So let's draw a diagram. This is the 30 meters. And it requires 1.5 seconds to travel that. That's the ground. And a certain free-falling object. Let's make that 0. Let's make it positive down here. It's going to go that way. And we're trying to find this entire distance. Okay? So this is a multi-part problem. First, let's just define what we already know. So the acceleration is 9.8 meters per second squared, and we know that for this particular problem, or the first part of it, the final velocity, because it's right before it hits the ground, it's like right here, would be 30 meters divided by 1.5 seconds, which gives us 20 meters per second. That's simple, easy math right there. Alright, so the first step of a problem, we have to use this kinematic equation. So the difference in x, so we're trying to find the initial velocity. What the velocity was right there is equal to velocity of initial times time plus 1/2 acceleration times squared. So we know that's 30 meters. We don't know what that is, but we know that's 1.5 seconds plus half times acceleration, that's 9.8 meters per second squared. We know that's positive, it's going that way, and time is 1.5 squared. Let's just plug it in. 1.5 seconds, what's the initial? So we know that this is 1.5 seconds and squared, so that cancels out. So that's going to be 1/2 times 9.8 times 1.5. 7.35 meters. Oh, sorry, no. 1/2 9.8 1.5 squared. Yeah, that looks more. 11.025 meters. So since these are both meters and we need to get what this is, whatever the initial velocity is, I'm going to subtract that from 30 meters, get 18.975 meters, and then divide that by the time. So 18.975 divided by 1.5 seconds gives us 12.65 meters per second. That is the initial velocity. That's the velocity. It was right there as it kept falling. So now that we know what the initial velocity is, we have to find this entire length. So we want to use the same kinematic because it already gives us this, and we already know everything else except for time. But I'll get to that later. So let's change it to a different color. The second equation, we would use x equals velocity initial time plus 1/2. So the same equation, but we're going to have to derive something else from it because we don't know what this time is. So what do we know now? We know that the initial velocity is going to be 0 meters per second squared because that's the velocity when it began, and nothing moves, as you're holding it or whatever. That's going to be 0. So we don't have to worry about this time because this is going to be 0 anyways. But what are we going to do about this, right? So acceleration is defined as velocity over time. If this kind of confuses you, you can make sort of a chart like this when we do for like Ohm's law, for example. And we look at what we have. So we have acceleration, that's 9.8 meters per second squared. We have the velocity, that's what we just got, but we don't have time. So what can we do to get time? We can just do time equals velocity over acceleration, right? Simple enough. So we can do that. Acceleration times velocity over squared. And once we get that, we can say that's 0, so we don't have to worry about that. 1/2. This is actually velocity squared over acceleration squared, right? So we can cancel one of the accelerations out. Velocity squared over acceleration. And then that's simple plug and play there. 1/2. We already got the velocity, 12.65 meters per second squared. Oops. And the acceleration is 9.8 meters per second squared. So we just need to cancel that, cancel those, get, let's just get my calculator out. 1/2 or 0.5, 12.65 meters per second squared, 9.8. Oops, divided by. Oops, 9.8. And that gives us 8.164. Let's just say 8.16 meters. But we are not all done. Let's shift it up a little bit. Yeah. So what we got from here was this length, right? Because we didn't factor in the 30 meters right here, or it would have been useless to find that. So another way you could do this is actually just add 30 meters or subtract 30 meters from this, because if you were trying to find the whole thing, you would subtract that and then you can just add it in. So the final answer would be 1.86 meters plus 30 meters. If you didn't want to do the last step like me, you could have just made this equation minus 30 meters and then equals, 1/2 velocity squared over acceleration. But we didn't do that. I wanted to keep it simple. So this is equal to 38.16 meters, or about 38.2 meters. That is our final equation, our answer. So now we know that as it was falling, it was 9.8 meters per second squared, the acceleration. From the last 30 meters, it was 20 meters per second. During this time, it was 12.65 meters per second. At the beginning, it was 0 meters per second. The whole thing was 38.2 meters, and the last 30 meters. All right. Thank you on number 45 of page 50, chapter 2 homework of Greenberg Physics without Mr. Greenberg.